No regret algorithms for unconstrained online convex optimization. Here's a brief overview of what our slides are going to cover. There's a background, problem setting with the notations and problem statement, gradient descent with increasing learning rates, which goes over analysis in one dimension and analysis in n dimensions. Then we have the epoch-free algorithm, and then we cover the lower bounds. And then at the end, we'll cover future uses. Online prediction. Given an attribute vector, the algorithm produces a prediction. As we can see from the image here, we're given the attribute vector, we feed that into our algorithm, and then that gives us a prediction. We compare this prediction to our adversary label, and this comparison is then put into our loss function, and the prediction is penalized. Current other algorithms fail to achieve sublinear regret unless the comparator point x is known in advance. New algorithms are presented, no prior knowledge is needed for them, and they offer near optimal regret bounds. Constant regret with respect to x equals 0 achieves a stable level of performance regardless of the number of rounds. And for future use, OCO stands for Online Convex Optimization. Some more background. Algorithm adjusts the learning rates with the number of rounds and the sum of the gradients seen so far. It starts with small learning rates and increases the learning rates if needed. It guarantees regret bound with respect to x equals 0. Constant regret is guaranteed. Applicable to other online OCO problems where the fixed feasible set is not required. The unconstrained experts problem and portfolio management. Typically when given n experts, we choose one expert I. When it's constrained, we choose more than one expert I. So as you can see in the bottom left, this is the typical problem. The one on the right is what our paper goes over, the unconstrained experts problem. When it's unconstrained, we choose from more than one expert I, and we place bets on each expert. The negative values bet against, as you can see from the red. The positive value bet for, as you can see from the green. We place these bets to achieve the highest possible reward. Our results are that multiple investments can achieve exponential wealth. The notation and problem statement. Our time around index is t. We have a set number of experts, x. Here is our reward function. Our cumulative reward is right here. Next is our regret. And our goal is to maximize the cumulative reward. Comparison of regret bounds. We formalize matching bounds, both upper and lower, for unconstrained OCO problems. No required previous information is needed. We will focus more on the reward, and with reward doubling, this helps guarantee the optimal regret bound. Has robust parameters without needing details about the comparator point x. Reward doubling algorithm is not dependent on traditional parameters. Constant regret even where the other algorithms fail, and only one offers sublinear regret. This jumps back to the origin frequently. This may be undesirable, but currently guarantees constraint to origin regret x equals 0. Comparison of regret bounds. Here is our theorem. The proof. We plug reward lower bound into the definition of regret and derive equal to 0. And in the unconstrained setting, it is sufficient to provide guarantees for general n-dimensional online convex optimization based on the 1D results. And now I will hand it off.
Okay, so let's talk about the method we want to use to solve this problem. Okay, as described in the expert problem, the xt and gt has n dimension because we have n experts, right? But here we want to start from something easy. That is, we want to start from the one-dimensional case where the x and g's are all scalars first. So on each round t, the unconstrained gradient descent placed xt equals to this eta times g times the sum of g from 1 to the t minus 1. So basically, this directly follows the ideas of the gradient descent, and the cumulative reward is the sum of gt times xt, and t from 1 to the capital T. So if you plug in the formula of this xt equals to eta times g from 1 to t minus 1, you can directly get this interesting result. That is, the reward is actually equal to 1/2 times eta times this g square minus h. So this capital G is the absolute value of the sum of g from 1 to t. And this capital H is the sum of the square of the gradient. And the interesting thing is that this cumulative reward is actually independent of the order of the GT selected by the adversary. And this actually gives us the intuition of our method. Because our goal is to maximize this cumulative reward. So when we look at this cumulative reward more carefully, we can find that actually we want to increase the value of this eta when we have a larger value of this g squared minus h. On the other hand, if this g squared minus h is negative, we want a small eta to cut off the loss. So this is basically the idea of the reward doubling, right? Because the doubling means that we want to increase this learning rate eta when the g squared minus h is met with some conditions. Okay, so however, some existing online algorithms update the learning rate eta based only on this h, which is the sum of the squared gradient. Because this h is actually monotonically increasing. So the weakness of these guess and doubling tricks is that you neglect the impact of this g, which is the absolute value of the sum of the gradients, because the gradients actually take the value from -1 to +1. So this g is very likely to increase or decrease. Okay? So this is our motivation of our method. That is to update this eta by utilizing both g and h, and increase the learning rate with larger g squared minus h. So this is our motivation of this guess and doubling tricks. Okay. And now we will give our description on this reward and doubling algorithms. Okay. So still, we consider the one-dimension case first, right? And even more, we want to simplify our problem further with the strong assumption with this upper bound of the h. So we assume that we have start with some initial learning rate eta 1, and we have known the upper bound h bar. So we start from this small initial learning rate eta 1, and at each point, we increase our cumulative reward. And at a certain point, when the cumulative reward meet with some certain conditions, we can double the learning rate eta. And we call each stage an epoch. So at each step t, we first play xt and collect the cumulative reward. And then we use this cumulative reward to compare with the eta I times this h bar, the upper bound. And if the cumulative reward is lower than this upper bound, then we keep the same learning rate, and we update our xt minus 1, our xt plus 1 by add up this eta I times gradient. On the other hand, if this cumulative reward exceeds this upper bound, then we return to the original point and forget all the historical gradients except the latest one. And we double the learning rate and step into the next epoch. So we can find that at each epoch, we double the learning rate and forget the historical gradient in the previous epoch. Okay, so this is the idea of the reward doubling. And so actually it can give us a lower bound of the reward. So to derive this lower bound, actually, we take a look at this a, right? This a equals to log 2 over square root of 3. So when we plug into this exponential exponential function, we will find that actually this lower bound is related to the 2 to the power of k. And so to find this k, we use this constraint that qi should be less than this eta h, and you can directly get this lower bound. But we won't talk much about this lower bound because of the limited time. Okay, and also remember that we have a conversion between the reward lower bound and the regret upper bound. So when you get this lemma on the reward lower bound, immediately it gives you the upper bound of the regret. And actually, the regret of the online gradient descent with the fixed learning rate is bounded by the order of r times the square root of t. And if you choose h bar equals to t, right, because the each gt takes value between the -1 and the 1. So if you choose this h bar equals to t, and this eta 1 is 1 over t, then for any feasible any feasible radius of the radius r, the worst case regret of this algorithm is at most this guy. Okay. So until now, we're talking about, we have a strong assumption on the upper bound h bar. But one question is that, what if we don't know the upper bound? What can we do? Then it gives us the motivation of this reward doubling guess algorithm. That is, we guess the upper bound, which takes the value of this guy, which is h bar equals to 2 to the power of I minus 1. And the remaining thing are the same with the simple reward doubling algorithm. So at each epoch, we do the update and we collect the cumulative reward, and then we compare this cumulative reward with this guessed upper bound. And then if this guessed upper bound is smaller than our cumulative reward, then we double the eta. Okay. And similarly, use the same trick, you can derive an upper bound on this regret. So actually, the proof just simply plug in all the definitions and expand every terms in the equation, and you can get what you want. Okay. So now we have talked about the 1D cases, but at last we want to extend our algorithm to n-dimensional cases. And luckily, we are dealing with some linear models. So in linear models, when we extend the scalar multiplication to vector multiplication, we just need to add up all the element multiplications together, and it will give us the result. So that means that we just need to repeat each reward doubling guess algorithm for n times, and then put them together. Then it will give us the n-dimensional reward doubling algorithm. And so this is the description of the n-dimensional reward doubling algorithm. And we can see that actually this regret upper bound, it looks very similar to the one-dimensional case upper bound, right? We just increase the dimension. We just sum. Actually, we just need to sum n elements of this upper bound and sum them together. It will immediately give you this upper bound, right? You replace this r. R actually is the upper bound of one-dimensional case. You replace this r by this x star norm. Okay. So, but in the guess and doubling tricks, we need to do the updates in several epochs. But as we said, this G can both increase or decrease. So sometimes this guess and doubling algorithm may fail. So is there any more powerful algorithm that can solve this problem once for all? We don't need to update in several epochs. So the authors tell us another algorithm called the smooth reward doubling algorithm. And luckily, you can directly use the sum of this gradient as the together to derive the next xt you want to play. So simply, actually the algorithm, the structure of the algorithm is very easy to understand. That is, you play this xt plus 1 equal to this eta times a signal function times a fixed function with respect to gt and t. Okay, so if this gt is positive, then you just keep the same value. If gt is negative, you just need to flip the sign of your result. But unfortunately, they did not give us some very detailed explanation on how to find this objective function, how to find this fixed function, like 1 over t to the power of 3 over 2 times this exponential value. And I think that is the weakness of this paper, because this is what they want to explain, but it looks like they cannot explain their designs and intuitions very well. Okay. And on the other hand, they also give us a lower bound of the regret. And so it shows that the algorithm regret is at least this guy, this the linear coefficient times the this x and times the norm of x and times the square root of the log over the norm of x. And similarly, for the n-dimensional case, you just need to sum n elements of each one-dimensional lower bound together. It will give you the lower bound of the n-dimensional regret. Okay, so that's all for the method they proposed. And I think there are still several weakness or confusing points lies in their paper. The first of all, actually, when they're discussing the reward doubling guess algorithm, they did not give us the formal solution of this algorithm. They just draw a plot of the algorithm, but they it is hard to explain how they guess the upper bound and why they choose this and why they choose this to guess the upper bound. And the second thing is that they also didn't give us sufficient explanations and proof on this smooth reward doubling algorithm. Actually, I think this is the most important thing in this paper, but it looks like it is very hard to explain their intuition and their design and intuition on this fixed function they choose at this decision-making function they choose. So for the potential applications of this, online tuning on the learning rate, I think it shares similar ideas with the learning rate decay trick we use in the deep reinforced learning. So in deep reinforced learning, we want to decay the learning rate when the training process goes on. Because so here we use the decay trick because we convert the reward into the loss function. Okay, and and another application is that this paper is totally built on the linear models, the simplest linear models. But what if the things become more complicated? Will this result holds? That's a remaining question. And also, they only talk about the robustness and the power of their method, but they ignore the analysis on the per round time complexity. So it could be that their result is very powerful, but it costs much computational or time complexity. But then that is a sacrifice of their output. Okay. So this is all for our presentation. Thank you.